Okay, let us start. Welcome to Motion Planning lecture number 2, and thanks for coming at this early hour. Today our topic will be the structure of configuration spaces, and we will talk about topology, metrics, and constraints, which you can apply on those configuration spaces. But before I dive into this, I just wanted to introduce myself. So my name is Andreas Ortey. I'm officially a staff robotics scientist at Realtime Robotics. Realtime Robotics is a startup from Boston, and one of our missions is to create one of the most efficient motion planning frameworks out there, especially for industrial automation and also for cases with multiple robots. And I also did a lot of research on abstraction hierarchies. So as you will see later on in the course, motion planning, the deeper you go, the more you find out that it's actually pretty hard to do. And so one of my main research focus was to find good abstractions for motion planning so that we can solve like simplified problems and then use solutions to those simplified problems to actually solve the whole problem. And this torus here shows a simplification from a torus to a circle, and this is something which we will look at in one of the last lectures when we also talk about multiple robots, and we will see what kind of problems we have when the configuration space becomes super huge. Okay, that's all what I wanted to say about myself. So for this lecture, of course, if you have any questions or if you feel that I'm going too fast or too slow, then just raise your arm. And feel free to always ask questions whenever you want. And with that, I want to start. Just a small recap from last week. I guess you all heard about motion planning, which is basically just the task of moving robots from A to B. And I guess you should have seen that this is really fundamental to almost all robotics applications, especially to automation, to autonomous driving, healthcare, and of course games and animation. And some of the terminology from last lecture were like configuration spaces, degrees of freedom, and configuration map. And I will assume a little bit that you already are familiar with that. And today I want to go more into depth about configuration spaces, and I will talk a bit about topological spaces. This is basically how you construct configuration spaces for arbitrary robots. Then I will talk about metric spaces, which is basically about computing distances on configuration spaces. And then finally, I will talk a little bit about constraints, which you can apply on configuration spaces to make your robot move in such a way which is required for your task or how you want to move it. Okay, and with that, I just wanted to step a little bit back and just talk about the general motion planning problem. As we also discussed last time, so motion planning is basically, you can see it as a black box, and as input to this black box, you get a robot and some obstacles. Usually you get a start configuration and a goal. And what you want to achieve is basically a collision-free path, which goes from start to goal, which moves the robot in such a way that it doesn't hit obstacles and adheres to other constraints. If I would talk about one of the main ideas in motion planning, then I would say this is really the most fundamental idea for motion planning, namely that any robot can be modeled as a point in a configuration space. So this was basically an idea which comes basically from physics and which was introduced to motion planning by Thomas Lozano-Perez, which is this guy up here. And so what he basically said that instead of constructing motion planning algorithms for each robot individually, instead you can just see motion planning as a problem of a point in a configuration space. And so this means basically that we have transformed the motion planning problem to the problem of planning in a configuration space. And so I would say this is really the main idea underlying everything in motion planning. And so this is really the most fundamental thing. And I think, if you take just one thing away from this course, then I would say it's this idea that you can just plan everything in a configuration space where a robot becomes just a point. And yeah, to just visualize this a little bit and give you an example of how this actually looks like, I just have here a small animation. So what you can see here on the right is actually a small 2 degrees of freedom robot. And this robot can rotate around the middle point here. And it can also rotate around the second point here. And the robot is here in its workspace, and there's a small obstacle here in gray. And on the left here, you see the configuration space of this robot. So the configuration space is basically the joint angles of this robot. And a point here is basically representing a specific configuration of this robot in this workspace. So you can see here, if I move this point around, then the robot also moves around in the workspace. And in the configuration space, you have 2 regions. One region where the robot can just move around, which is this white one. And we have also a gray region, which is basically all the configurations which are in collision with the obstacle. So if I go here into the gray region, then suddenly the robot is also in collision with the obstacle here. And so this configuration space is, of course, dependent on the position of the obstacle or of the objects here. So for example, if I move this object a little bit to the right, then suddenly also the configuration space transforms. And so for example, if I move around in this configuration space here and I come into this gray area, then I'm in collision here, but you can see that this area is much smaller, and I would say planning when the obstacle is a bit farther away is of course a bit easier to do. Okay, this is just a small animation to just show you this whole idea of transforming a problem with a robot from this workspace here into the configuration space where the robot is just a point. And now you can just do everything what you want in this configuration space. And there are some implications. So one implication, of course, that this configuration space is a general purpose modeling tool for any robot. And also, we could construct one algorithm which could basically solve every problem. And with every problem, I mean you have any kind of robot, you have transformed it into the configuration space, and you could think about just having one algorithm which can solve any point robot in the configuration space. And this means, of course, that if you want to move robots around, then, of course, you need to really understand configuration spaces. And this is what we will do today. So, goal for today, understanding the structure of configuration spaces. And as I already said in the beginning, there will be 3 topics. First topic, topological spaces, where we will just model configuration spaces. So we will look at different robots which have different joint types, and then we will see how this actually translates into configuration spaces. Then the second topic, metric spaces, where we'll talk about distances in configuration space. And finally, we'll talk a little bit about constraints, the topic of feasible configurations, and also something which is super important, of course, is collision checking, because one of the most important constraints is, of course, that you are not in collision with any obstacles with your robot. Okay, so far, any questions? Yes?
Could you find the slides on ICE?
Yeah, we will upload it. So it's not yet uploaded? Okay. All right, any other questions? Cool. All right, so then I will start with the first topic, topological spaces. First of all, what does topology actually mean? So the etymology or the word origin of topology comes basically from topos and logos, which means topos, place, region, or space, and logos is study. So basically you can translate it as a study of space. And when you think about topology, then usually there is this mathematical definition of topology, which is basically the study of properties of geometric objects invariant under continuous transformations. And very often in introduction courses on topology, you see this picture here, which basically shows a donut and a coffee mug. And so those two types of objects, they are equivalent for topology because you can transform this donut here by just bending and deforming it into this coffee mug due to several steps here. And in topology, you would study what kind of properties of those objects remain invariant when you do this transformation. And so one of those properties is, for example, this hole here in the donut, which remains over all the transformations here and which also remains in the coffee mug. So that is how you approach topology from mathematics. And how does it actually help us in robotics? So for robotics, the motivation to use topology is basically to model configuration spaces of arbitrary objects, of arbitrary robots. So for example, you have a very complex robot like this Atlas robot here from Boston Dynamics, and you want to somehow translate it into configuration space so that you can just run our algorithms. And the way to go there is to basically understand how you can translate all the possible joint types which this robot has into different mathematical spaces and then put them all together to construct configuration spaces. And I would say the main idea of topology here is really that topology is a tool to categorize spaces. And so as a classification tool, it basically answers some very important questions about configuration spaces. One would be, what kind of space is actually associated to a given robot? Which robots have topologically equivalent spaces? Because if you know that two robots have the same spaces, then planning for them has roughly the same computational complexity. And also, we can answer questions like how do two motion planning problems differ? And also, in some cases, what is actually the computational complexity of a given category of spaces? So we will not go too much into computational complexity here, but yeah, I just wanted to tell you this, that this is also used for this purpose. Okay, and yeah, for motion planning, the relevant topics which I want to talk about today in topology are one, how we can actually classify spaces as equivalent, how we can combine spaces into compound spaces, and then finally how we can assign spaces to robots. And yeah, let me start with the equivalence of spaces. So something which is super important, if you have like 1,000 robots and they might all look different from the outside, it can still happen that they share the same underlying topological configuration space. So you see here a lot of different robots from different manufacturers. They all look different, different colors, different lengths. But if you actually model them into the configuration space, you will see that all those spaces look practically the same. And this means that planning motions for those robots is also, basically from a computational point of view, the same. And that is really a great way to abstract away details of a task and of a robot and really concentrate on the computational challenge of making robots move from A to B. And to say if two spaces are equivalent, the correct way to do that is actually to use this mathematical definition of a homeomorphism. Basically, we say in topology that two spaces are equivalent if there exists a homeomorphism between them. And so, of course, the question is, what is actually a homeomorphism? So let me give you a small definition. We will also go into some examples shortly. Okay, so a homeomorphism is basically just a mapping between two spaces, x and y. And a homeomorphism has some certain properties. One is that it's bijective, one-to-one and onto, which means So every point in a space X has an equivalent point in space Y, and you can just move between them. And also this mapping needs to be continuous and has a continuous inverse. And so if you actually can find a mapping between two spaces, then you can actually say that they're equivalent or homeomorphic. So this is basically just a word for saying that two spaces are topologically equivalent. And the intuition of having this homeomorphism is basically that you can squeeze, stretch, or bend the space, but it still remains equivalent under topological considerations. And here are some examples. So this is a small exercise for you. You need to find out which spaces are actually homeomorphic, which means you are not allowed to actually cut holes, tear the space, or glue stuff. And there are 6 examples here. And I will give you like a minute or so to just look at them, and then we will go through them, and you can tell me which ones are actually equivalent under the definition which I just gave you. Hello. Okay, so can someone tell me if A is actually homeomorphic, if the line and this squiggled line are the same?
I would say they are.
Yes. So basically you can just transform them into each other. So there is really a bijection between every point on the line and every point on the squiggled line. So those are actually equivalent. What about B? Yes.
I would say they're not equivalent because like the line is just one-dimensional, but
The disk?
shape is two-dimensional, and so you can only map in one direction.
Yeah, that's correct. So whenever you actually need to map the disk onto the line, you need to like squish several points together, and then you lost the information which points are actually grouped together. Okay, C. Yes.
You would have to glue something together.
Yeah, exactly. So you would basically have a singularity here at the endpoints where you have a discontinuity, and you would glue them together here in the circle, and so you would basically lose this continuity. How about D? Is that actually equivalent?
I would say it's not equivalent.
Why?
Because yet again we have like these different dimensions.
Yeah, exactly. So the same reason S and B applies here. That's correct. And what about E?
I think it is, because you can sort of squish the square into a circle shape.
Yeah, that's correct. So you can basically find a mapping which maps every point here from the disk to the square. And how about F? Is that equivalent? What do you think?
No, we are cut holes.
Yeah, exactly. So basically you would have to like glue everything here on the inside of the circle together, and then you would again lose some information, and you have this discontinuity. Okay, and here are the answers, just when you go over the slides again. Okay, so now that we know how to actually say that two spaces are equivalent, we also need some prototype spaces to construct configuration spaces, and I would say the most fundamental ones are really the line, the circle, and the disk. Here I wrote down how you actually construct them, so I think you are familiar with that one. Something to keep in mind is that we have a naming convention here, so we always write a symbolic name and on top here the number of dimensions. So the disk here you see already has dimension 2, means 2 parameters are required to describe the disk, and for the circle and for the line segment you only need 1 parameter to describe it, so it has 1 dimension. And if you want to really dig a bit deeper and understand why actually 2 spaces are equivalent, I would suggest that you also try to prove simple cases. So one simple case is, for example, that proving that the line, the real number line R1 and the line segment from -1 to +1 are equivalent by showing that this function here is actually a homeomorphism, which makes those spaces equivalent. Okay. So now that we have prototype spaces, we also need to combine spaces together so that we can construct bigger configuration spaces for bigger robots. And that brings us to the topic of compound spaces. And so the motivation is, of course, if you have a large robot like this Atlas robot here, it has a lot of different joints. To each joint you can assign a space, and then you have to somehow put all those spaces together. And so the question is, of course, how do you do that? And for that, the most fundamental idea is, of course, that you take the Cartesian product, which is, if you're given 2 spaces, x and y, then the Cartesian product is just defined by taking the tuple of all possible combinations of x and y coordinates. And for me also a good intuition is that for every element of a space x, you attach a copy of space y to this element. And by doing that, you can actually construct larger spaces. So for example, you can construct the plane R2 by just combining 2 lines together. So basically for every point on a line, you attach another line, and you do that basically for every point, and this gives you the plane. The same actually applies for a cylinder. You can have this line segment here and a circle, and you can just attach 1 circle to each element here, and this gives you a cylinder. Something to keep in mind that if you actually attach 2 circles to each other, then you get not the sphere, but instead you get a torus T2 in this case. I think it's very instructive to really think a bit deeper about why this is actually the case. So I don't want to go into details here. And then 2 questions for you. What kind of structure do you actually get if you take the disk and take the Cartesian product with a line? Anyone an idea? Yes?
You get a kind of filled cylinder?
Yeah, that's correct. And how about you do the same, but this time with a circle?
You get a donut?
Yeah, so basically a filled torus. Yeah, that's correct. Okay, and now we go a little bit more towards more robotics-related spaces. So the circle is already a very good space for describing a revolute joint, basically a joint which is just turning infinitely. R1 is a good space for describing a prismatic joint, for example, a drawer opening, something like that. R2 could be the space of a planar disk robot, which is moving around on the floor. And for example, if you have a Roomba robot, one space you can construct here is R2 times S1, which is basically a disk robot with a direction. And then something which is super important, which we'll see almost everywhere in robotics, is spaces like those here, SE2, which is called the special Euclidean group. And SE2 is basically just this set here of R2 times S1. I also wrote down here why this has this weird name here, but if you don't want to dive too much into the topic here, you can just take this as a shortcut. Basically, this is basically just all the transformations of a rigid body in 2D. And then for robotics especially, those 4 spaces are super important. SO2, this is basically all rotations of a rigid body in 2D space. This is just represented as a circle. Then we have SE2, what I already mentioned, which is all rotations and translations of a rigid body in 2D. And we have the same also for 3D. We have SO3, all rotations of rigid body in 3D space, and SE3, which is the same but for all rotations and translations. Yeah, any questions? Okay, and one of your homework will actually be to classify those joints which you have here and tell us what are actually the correct topological spaces attached to each joint. So I guess Revolute and Prismatic are pretty easy, but the other ones you have to think a little bit more about how they actually move and what kind of space is actually behind them. Okay, and now that we know a lot about topological spaces for robotics, I just wanted to show you some topological spaces in the wild on real robots, how actually configuration spaces look like there. So this one here is a standard industrial manipulator arm. It's called Panda by Frank Amica, and it has 7 degrees of freedom. So there are basically 7 rotational joints here. And so the configuration space of this one is R7. And another question for you, why is that actually R7 and not S1 7 times? So why is it just line segments and not a circle? Even so, those are actually rotational joints. Anyone an idea? Yes.
Maybe because like each joint only has a certain range where they can move and they can't just rotate over and over.
Yeah, exactly. So you basically have, not a full circle, but just a half circle or something, and then this is basically equivalent to a line segment. That's correct. Then yeah, some examples of SE2 are of course this Roomba robot moving around the floor and having also a direction, and of course a car can also be described by SE2. Of course, for a car you would have some other elements like velocity, acceleration, so the configuration space might be a bit more complicated in reality there. And yeah, so this one is also pretty famous robot, PR2. And PR2 has 31 joints in its upper body here. And it can also move around on this platform. And so you have actually a combined space of SE2 times R31. And so you have here a fixed space manipulator robot plus a mobile base. And then, of course, for flying objects, you have the space here SE3, which I already described, which is basically all the motions of a rigid body in space, and which is a combination of R3 for the translation of this drone, and SO3, which are all the rotations of this drone in space. I guess a lot of you are already familiar with Euler angles, so usually SO3 is represented by pitch roll yaw, which describes all the rotations around a point. And here, a more fancier robot where you have a drone and you have also a mobile arm which is attached to the drone. So you have SE3 for the drone for rotation and translation, and you have R6 for 6 degrees of freedom arm which is attached to the robot. And so this would be the configuration space of this robot here. so what you should take away from topology is that really every joint type has an associated mathematical space. You should also have some knowledge of how to put those spaces together using the Cartesian product. And yeah, I hope you are able to construct also a configuration space from a given robot and from the joints of a robot, and to determine if two configuration spaces are equivalent. And before I move on, just any questions? Yes?
Maybe about like how do you represent the joint limits exactly? Because for the Franke-Amico, you just like I would guess that the actual space is a subspace of the like R7 space because the joint limits don't fill the full R.
Mm-hmm.
So like, do you usually represent that in the configuration space as well, or just kind of take the whole?
Yeah, so basically, of course, it would not be the whole line segment. But what is really nice is that we can talk just about this real number line because it's topologically equivalent to any line segment. So even if you have like some joint limits between plus pi and minus pi, you can still say that this is equivalent to the real number line topologically. And you can just talk about having the real number line here as a space associated to this. Does that make sense? But of course, if you want to program it, of course, you have to have the limits there, right? So you have to say, okay, this goes from here to here.
Okay, and if it's continuous, then we can't represent it as a line, but as a circle.
Yeah, exactly, because every time you rotate, you come back to your first point. And as we will also see for distances, and some things change. And then you can't just represent it as a line anymore. Yeah. Yes?
In the exercise, we said that the drone has actually, for each rotor, 1 degree of freedom. But now we said that it has only like 6 degrees of freedom, like a normal rigid body in space.
Mm-hmm.
Like, how do the rotors relate to the joints of a robot arm?
Of a robot arm?
Like, I think we defined it in the exercise like that. Like, so that's why I'm asking why we have 4 rotors, but we have
Mm-hmm.
only like 3 degrees of freedom for the rotors.
Yeah, so of course there are different ways of how you can model a robot, and so I don't know exactly how you modeled it in the exercise, but of course if the rotors, for example, are bigger, then of course the position of the rotors in space is actually important because you want to know if they are actually in collision with an object at a specific configuration, and then it would make sense to actually take them explicitly into account and model them basically here also as rotations. Yeah, does that make sense?
Yeah, it kind of both makes sense. So,
Yeah. Okay, yeah, so of course you have different ways of how you can define a configuration space. So I guess this is really the most naive way of how you can define the configuration space of a drone, but of course there are other ways of how you can do it. And of course, Wolfgang is an expert in drones, and so his definition of the configuration space of a drone is, of course, I would say the more accurate one, so you should definitely go with that one. Okay, any more questions before we move on? Cool. Okay. So next topic up are metric spaces. So far we constructed configuration spaces, but it is also super important that we know how to measure distances in configuration space. And so why is that, of course, important? Because we want to know how far actually are we away from a goal, how far do we have still to go towards a goal. And this is also lies at the really heart of informed versus uninformed search. So Uninformed search is basically something where you don't have distance information, where you just take configurations and you don't really know how far are you away from your start, how far are you away from your goal. And this is really like, yeah, black box optimization. But in informed search, you have actually a distance function. You can say, okay, I'm this far away from a goal, and so this is why you can make more informed decisions at every point. In your configuration space, you can basically go into directions which you think make more sense because they bring you closer to a goal. And this, of course, answers questions like where should we explore next. So having a distance function is super crucial. So you will learn later on that sometimes it's also possible to just plan without a distance function. But if you can define a distance function on a configuration space, you definitely need to do it, and you should do it. However, there are some problems in defining distance functions. So one problem is how you define distances on non-Euclidean spaces. So if you're just having a configuration space which looks like a cube, then of course you take just a Euclidean distance and you're done. There's not much else to do. But if you have like weird configuration spaces like the torus here, then you have to really think a bit deeper about what kind of metrics, what kind of distances you actually apply on this space. And the second problem are what do you do if you actually combine different spaces? If you have bigger configuration spaces, how do you actually define a metric or a distance function on those spaces? And something which I also want to stress is that metrics are really a choice. So if you have a space, this does not really dictate the metric, but instead you are the one who can choose the metric. And this really depends on task requirements, objectives, and also computational cost of computing a metric or a distance function. So then the question is, of course, how do we choose a metric? And I would say the ideal option to choose a metric is really the true distance between points, including constraints. But of course, this is very difficult to obtain, and usually this is basically equivalent to just solving your whole problem and generating the best motions. So that is why the default option is usually to have the length of the shortest distance path, basically the geodesics in space. And also this decision is based on low computational cost. So if you have a distance function which is very accurate but also very costly, then this is usually not a good idea. And also very often you want to promote better quality paths. And this is also something which factors in the decision of what kind of metric you choose. Okay, so far I did not yet give you a good definition of a metric, so let me just get this out of the way. So a metric space is basically a topological space plus a distance between points, and this distance between points, this function is called a metric. And so a metric space is basically a topological space X plus a function D, and this function D takes as input two configurations, and it produces an output, a real number, a real positive number. And there are three constraints on this distance function. One is this identity of indiscernibles. So basically, if you have 2 points which are equivalent, then the distance should also be 0. And if the distance is 0, then those points should also be equivalent. The second one is symmetry. If you go from one point to another and you have a distance between them, then going the other way around should produce also the same distance. And finally, you have the triangle inequality. So if you go from one point to another, then this should be the shortest distance between them, and there should not be a shorter distance by visiting another point in between. I would say those are really like common sense assumptions which you do on distance functions. Let me give you some examples of metrics. So I guess the most well-known metric is, of course, the Euclidean metric, the straight line distance. So if you are in a Euclidean space, then of course, if you have 2 points, one distance which you can choose is just a straight line between those 2 points. I guess you have all seen this, and this is really the most commonly used metric on Rn. However, sometimes you want to choose different metrics. One also famous metric is this Manhattan metric, where you basically take the sum of absolute values of each dimension, which means you just sum up over all the dimensions and you just take the absolute value. And what this represents is really like this zigzag motion. You see here, this is a picture of Manhattan, and in Manhattan you can just go from one point to another in a straight line, but instead you have to follow this square-like array of streets, and this basically gives you just directions along coordinate axis. So you can either go along an x-axis or an y-axis, and this is how you actually move from one point to another. And this is something which you can also use as a metric. And so questions, of course, why would you choose something like that? And this could come just from your problem definition. For example, you might have a robot where each joint can only be actuated individually, or you have, for example, a set of objects and your robot can only move one object at a time. And in that case, it actually makes sense to only move along one coordinate axis, or in this case here, one dimension where one object is located in your configuration space. Okay, and for non-Euclidean spaces, the metrics are a bit more complicated. So for example, if you have a circle, then of course this Euclidean distance breaks down. And because if you have two distinct points on a circle, like for example here you have one angle at this point and one angle here, then there are actually two paths to connect them. You can go clockwise or you can go counterclockwise. And so one good metric to define is actually to take the minimum of those two paths. And so one metric which you can define on a circle is this one here. It's just the minimum of the clockwise and the counterclockwise path on a circle. And yeah, to show you that this is more accurate compared to the Euclidean metric, here is another small example from the small robot which I showed you in the beginning. So we have here two configurations, both in a line here, one at minus 2.1 and one at plus 2.1 in x direction. And the Euclidean metric would just compute the distance between them as a straight line here and would tell us they are 4.2 apart. However, if you have the circular metrics, then you also take into account that this space is actually wrapped around on the other side here. And the circular metric would basically take both of them into account and would produce the more accurate value of 2.08 for this example here. Okay, so this is just a small example of circular metric and how it actually makes more sense on non-Euclidean spaces to think a bit more about what kind of metric you put on them. There are also other metrics which you can impose on a robot. One very important one is this workspace metric, which is basically the Euclidean distance of the most displaced point of your robot. This is what you can see here in this picture. So basically you have this triangle robot and it moves from one configuration to another configuration, and you want to just define the metric by the distance of the point on this robot which is displaced the most. And from that you can also create a metric, and this is something which you can define here as the max of all the points on the robot and the Euclidean distance between them. Right, and very often you don't do that for the most displaced point, but you choose in the beginning one point on the robot, for example, the end effector with which you are doing some task or so. Okay, and so apart from those metrics, which are really distance metrics, which you can define, there are also some exotic metrics where you are getting rid of some of the assumptions of a distance function. And they are pretty important for robotics because sometimes they can help us to create better paths or solve a problem much more efficiently than when we would just apply a normal metric. So one way to define a metric is also by using this pseudo-metric, where you just get rid of this first assumption of this identity of indiscernibles. So now it can happen that you have two identical points and their distance is not 0, or the other way around, you have 2 points where the distance is 0, but they are not equivalent anymore. And one example of that is the end-effector distance. So here we have a small 2D degrees of freedom robot, and you want to measure distances by the distance of this end-effector here of the robot, so the last point on the chain. And if you do that, there are situations where you have the same point in space, but there are different configurations which actually reach this point. And in this case, those two configurations have a distance of 0, but they are actually not the same configuration. And so those are actually violating the first assumption here. You can also violate the second assumption. This is also important for some robotic cases, where you get rid of symmetry, which means you go from one configuration to another, and you have a certain distance, but if you go the other way around, the distance is suddenly bigger or smaller. And yeah, some examples where this is actually important are dynamical systems. So for example, if you have a small airplane, and this airplane is just flying forward from one configuration to another, then the distance would be smaller than if this airplane needs to actually move backwards from one configuration to another, because it cannot just move backwards, it has to like fly around to go to the earlier configuration. And the second one are time-based spaces, where one of the dimensions is actually time. And of course, you can always go forward in time, but you can never go backward in time. And so the distance between going forward is something positive, but going backward is usually not possible, and so this would be infinite. And here it would actually make sense to have something which violates this assumption, and this is also something which we call a quasi-metric in this case. And then the third possibility here is that you violate this triangle inequality. One way you can actually do that pretty easily is by having a measurement-based metric. So for example, you have 3 nodes here, A, B, C, and the distances between them is 1 meter. So that could be like configurations of like a disk robot on a line. However, you can not directly measure this, but you have only like a very inaccurate measurement device. And for example, instead of measuring here the correct distances, instead you measure something like 0.8 meters between A, B, and 1 meter between B and C, and 2 meters between A and C. And so now the distance between A and C would be 2 meters, but the distance to go from A to B and from B to C would be just 1.8 meters, which is smaller. And in this case, it would violate the triangle inequality, but it would still be a good metric for cases where you have something with measurements. And violating the third assumption is something which we call a semi-metric. So there are basically 3 different ways of how you can violate this by just taking one away, and this gives rise to 3 different metrics. Okay, so now those were some examples of metrics, and now I just want to go a little bit into proving or showing you how you can actually prove that something is a metric. And that is pretty useful because motion planners can actually often exploit properties of metrics. So if you are really sure that your distance function has a certain property, then you can actually go to your motion planner and you can construct more efficient algorithms. So you can solve a problem quicker, and so on. And also it gives you the tools to decide or adjust a custom metric. So if you actually have the tools to prove something and you see that you are not directly a metric, but you can make small adjustments, then this is actually a good tool to have to make those adjustments and get to a real metric. And the case which I want to look at here is the Manhattan distance. So I want to just very quickly go through this process of showing how you can actually show that this Manhattan distance is a metric in R2. So the Manhattan distance, as I already showed you, is basically just the absolute value of the different coordinates in xy in your R2 plane. And if you want to show that this is a metric, you need to go through all those three requirements, and you have to prove each of those requirements. And if you can do that, then you can say, okay, this is really a metric. So we will just do that very quickly, just going through all three of them: identity of indiscernibles, symmetry, and triangle inequality. Yeah, the first one, you have to basically prove two directions. You have to say, okay, if two configurations have a distance of 0, then they are equivalent, and you have to also prove the inverse. You have to say, okay, if those two configurations are equivalent, the distance between them is 0. And so for the first case, you can just go over 4 cases here. So you can assume that the distance between is 0. Then you can show that those two equations here are 0 by going over 4 cases. Basically, the first case where the x components are smaller than 0, and then those 2 cases where the y components are smaller than 0. And the last case here where both of them are larger than 0. So yeah, I don't want to go much more into detail, but this is actually a nice exercise also for yourself to just show that this is actually true. And the inverse case here on the very bottom, there you have that you assume that those two configurations are equivalent, and then you can just go over them and say, okay, if they're equivalent, then the individual components need to be 0, and therefore this distance needs to be 0. So for this case here, we can actually say that this identity of indiscernibles actually holds true. Symmetry in this case here is actually also pretty easy to do. We can just use this identity of the absolute value, namely that the absolute value of a positive number is equivalent to the absolute value of the negative number. And this gives you here the symmetry in this case. And finally, for the triangle inequality, you can just write out this whole equation. You can do here one where you add a second variable in the second step here. You can rearrange things a little bit, and then in the end you actually get to this result here that the triangle inequality for the Manhattan distance is fulfilled. And in this case here you can also use this property of the absolute value. Okay, so I would say this is really something you should go over at home and just make sure that you actually can follow all the steps. And I think this is really a very important exercise because it gives you the tools to decide if a metric is actually a metric or if something is a semi-metric. And depending on that, you can go to your motion planner and exploit those properties of the metric. Okay, so the next topic I want to talk about are compound metrics, where you have different spaces together with different metrics and you want to combine them. And so one big question is, of course, how we can create metrics on Cartesian products. So let's assume that we have two non-Euclidean spaces here. We take the Cartesian product of them. How can we actually create metrics from those Cartesian products? And one straightforward way to do that is actually just taking the sum. And basically, if you have here two metric spaces where you have a topological space and a distance function, you can define a new metric space, which is a Cartesian product. And you can also define a new metric space by taking this distance function here, which is just the sum of the individual distance functions. And if you want to see that this is actually true, you have to also go over the same proof concept. So you have to go over the three identities here, over those three properties of a metric, and you have to prove for each of them that the sum of those two spaces is actually again a metric. And the way of how you do that is that you do the same as we just did. We first say, okay, let's prove the identity of indiscernibles. We assume that the distance of two configurations, Z and Z prime, is 0. And then we take this and show first that it follows that those two configurations are the same in the first step. And then in the second step, we assume the inverse. We say, okay, two configurations are the same. Let's prove that the distance between is actually 0. Okay, so yeah, I don't want to bore you so much with details here, so I will just go quickly over it. Yeah, this is definitely also something which you can do at home, and also one of the exercises will be to construct a proof on a metric. So I guess this will come in very handy for you to do this proof. Okay, and the consequence of all that is basically that taking the sum of individual metrics produces again a compound metric. So it's basically very easy to compute metrics on compound spaces. And to just recap that, first of all, what I said is that there's no single best metric for a problem. And I would say the default choice for metrics are geodesic-based metrics. So basically, you always want to try to find the length of the shortest path. And this choice is also affected by compute time. How long does it actually take to compute a metric? And by path quality, so what kind of paths are actually prioritized by a metric. And then finally, I've shown you quickly that compound metrics can actually be constructed by the sum of individual metrics. Okay, so I would say this is everything about metrics so far. And before I move on, any questions? You had a question? No. Okay. All right, then let's move on. Last topic for today are constraints. So very often you have a configuration space, you know how to measure distances between them, but we didn't yet talk about what happens actually for configuration space points where you are in collision with obstacles with your robot, or where you want to, for example, have stability of your robot fulfilled, and how you can actually apply them to the configuration space. So the problem is basically that the configuration space allows all possible motions of your robot, and some of those motions, for example, could lead to the robot doing some self-collisions here, or some motions could lead to the robot being in collision with an obstacle, and we would, of course, try to avoid this, and the way we do this is by putting some constraints on the configuration space. So depending on what kind of task you want to achieve, you need to restrict the motions, and you need to put whatever constraints you want on the configuration space. And here are some examples of some constraints which you could have for realistic robot applications. So for example, here we have one application where this robot arm needs to transport a box from one table to another table. And in this case, the robot should, of course, not collide with any external objects. The robot should not self-collide. And sometimes you have some valuable goods in those boxes here. And so sometimes you would also like to impose that the robot should keep its end effector in a certain orientation so that the box is not tilted in any way. For autonomous driving, you have slightly different constraints. You would, for example, want that your robot should avoid future car collisions. Your robot should maybe also keep the lane in which it is actually currently. It should not go to another lane and crash with the car here. So this scenario would have maybe different constraints than the one before. And if you have more complicated robots, for example, you have a walking robot, then of course this robot should not collide with itself or the environment, but the robot should also not fall down. And so you would like to have some static stability of the robot. You always want to be in configurations where the robot is not tilting or falling down. And all of those scenarios and all of those constraints which I just talked about, they can be formalized by just having a constraint function. And so the constraint function in a very naive way can be constructed as just a mapping from your configuration space to true and false, which basically tells you for each configuration in your configuration space, is this configuration actually violating a constraint or is it not violating a constraint? And if you have such a function, you can just build it into your motion planner and you can always remove those configurations where a constraint is violated, and you can just concentrate on the configurations where it's not violated. And we will look at how we can construct two constraint functions and how we can actually compute them. One are collision constraints, which I would say are the most important ones for robotics. And the second one are stability constraints, which are only important if you have like a walking robot, like a humanoid or a quadruped. But this is also something which is pretty important for a lot of applications, of course. Okay, and with that, let me start with collision checking. Let me give you a small introduction of how you can actually do collision checking for a robot. So what we want is basically having a function which is called isValid and which tells you if a robot at a certain configuration is collision free. So for example, if I'm in the configuration space and I'm at this red cross here, then I want my function to return true because this robot in the workspace is not in collision. And if I'm in configuration space and the red cross here is in the gray area, then of course I want my function to return false because here there's a collision between robot and obstacle, and so this would not be a physically feasible configuration. The outline for this collision checking topic will be that we will talk a little bit about representations, about computational complexity, and then we will talk about broad phase and narrow phase, which is, I would say, one of the most important approaches to collision checking. And then we will quickly look at the flexible collision library, which is basically one of the most important libraries to do collision checking efficiently. Right, so first of all, if we want to do collision checking, we need to have some kind of representation of our robot and our objects. And usually there are two common ways of how you can represent them. One are polygon meshes and the other one are voxel representations. So for example, if you know about all the obstacles which you have in your environment, then very often you can just create polygon meshes of those objects and you can just represent them as a set of triangles. However, if you are not yet sure in which environment your robot will operate, then usually a voxel-based representation is more important, where you just represent objects as sets of voxels. And so this is usually a very nice way to represent them because very often you have, for example, RGBD cameras or LiDAR sensors which can directly generate this voxel representation for you. And there's also this Octomap library which can take a lot of different input sensors and which can generate good voxel representations. Right, so what about computational complexity? So let's assume that we have n rigid bodies in our scene, and then collision checking would actually have a worst case complexity of O(n) squared, because it requires collision checks between all pairs which are possible between objects. And so if you have a mesh representation, you need to check every pair of triangles. And if you have a voxel representation, you need to check every pair of voxels on different obstacles. And if you have a very big or large scene with a lot of robots and a lot of objects, like this one down here, then this can become very, very complex. So for example, if you have a configuration for all those robots here, and you want to know if they're actually collision-free, then you have to take every object and every robot. You have to check for each of the links on the robot if it's in collision with this object here, and then you have to do the same for all the other robots. And then again, you have to do it again for the next object, for the next object, for the next object. And this is only for one single configuration. And you can see that this can become very inefficient very quickly. And so that is why we need to actually have more efficient, more smarter ways of how we can do that. And I would say one of the most important ideas here in collision checking is this broad phase versus narrow phase approach. So the idea is basically that you have a broad phase in which you are trying to prune collision pairs. And then you have a narrow phase afterwards where you try to really check if two collision pairs are in collision. And in this broad phase, you're just trying to figure out are those objects close to each other or are they far apart? And if they are far apart, then there's no need to actually check for collisions because they cannot be possibly in collision. And this approach can really lower runtime significantly. And I would say this is really the preferred approach for collision checking. And the idea here is that in the broad phase collision checking phase, you try to find out which collision pairs should actually be checked. And you do that by representing collision pairs as bounding volumes. And you only check if the bounding volumes intersect. And usually this is way simpler, way more efficient to do. And that is why the broad phase is much faster to do, and it can just prune a lot of collision pairs. And of course, this is conservative. So if the bounding volumes do not intersect, we can just prune them away. And if they intersect, we need to go to the narrow phase. And we have just do like a pre-classification of which collision pairs we should actually check. And in terms of bounding volumes, there are different ways of how you can do it, different choices. One is to just have a bounding sphere. So you can see here different ways of how you can represent a complex mesh. You can just draw a sphere around it. You can draw an axis-aligned bounding box, an oriented bounding box, a discrete oriented polytope, or just taking the convex hull. And so if you move into this direction, then you have a better bound. You get more accurate results. And if you go into the other direction, you get a faster test, and you need less memory to actually represent it. So and the choice of this bounding volume, it really depends on applications. So in some applications, it is super important to have just a sphere, but sometimes you need a bit more accuracy, for example, really representing it as a convex hull. Okay, and because convexity here is a very important topic, I'm not sure that everyone is actually familiar with convexity. That is why I just wanted to include this slide here to give you just the definition of convexity again. So the definition is basically that if a set is convex, if for any 2 points in the set, you can draw a line between them, and you can be sure that this line actually lies inside of the set. So in this picture here, you can see one set where you pick 2 points, and you draw a line, and this line is inside. However, if you have a shape where you pick 2 points, and the line is not strictly inside of the shape, then this shape is not convex anymore. So this is the definition here of what we use as convexity. And an important point why convexity is so important here is because almost all shapes are decomposable into convex shapes. And so that is why we can just concentrate usually on convex shapes. So yeah, wait a second. So in this narrow phase, we do exact collision checking for all pairs which have not been pruned in the broad phase. And yeah, this common strategy here is basically that we do convex collision checking between two pairs of objects. And this requires that we decompose every object into convex shapes. So yeah, as I said, most shapes are decomposable into convex shapes. And so, for example, if you have a complex shape like this rabbit down here, then by doing convex decomposition, you can often yeah, convert a very, very detailed mesh into a much simpler geometric form, which almost resembles the original mesh. And very often, so usually you can do that for almost any shape, and that is why convex collision checking is actually the thing which you have to do in the end. And the same is actually true if you have a voxel-based representation, because all the voxels are also convex. And so in the end, you have to also do convex collision checking here between voxels. And yeah, so this is something which happens in the narrow phase, where you do convex collision checking between convex objects. And the cool thing is that convex collision checking is actually pretty cheap. And we will look shortly at the GJK algorithm, which actually is the preferred algorithm to compute collision checking between convex objects. Okay, any questions about this general approach to collision checking before we go on? Okay, so yeah, this was the general idea. We have two phases, broad phase and narrow phase. And in the narrow phase, we are trying to yeah, do collision checking between all pairs of convex objects. And the way of how we do that is by using the Gilbert-Johnson-Curti algorithm, GJK. And I want to just quickly show you how you can actually apply this. So the GJK algorithm is basically, yeah, I would say the most efficient algorithm for convex collision checking. It was invented in 1988, and you can read all about it in this publication, a fast procedure for computing the distance between complex objects in three-dimensional space. And the assumption here, as I already told you, objects are represented as convex polygons, and we only need a algorithm for computing if two convex polygons are in collision. And the GJK algorithm originally only checks for polygon-to-point collision checking. However, as we will see shortly, we can reduce polygon-to-polygon checking to polygon-to-point checking. And I will show you how this actually works. Okay, yeah, let me just give you a small example of how this GJK algorithm actually works. So B here is a convex polygon, and A here is a point. And we want to know if point A is actually inside of this polygon. And the way the GJK algorithm works is by just randomly choosing three vertices in the polygon, creating a small triangle here, which is called Q. And then in this triangle, we try to find out what is actually the nearest point to point A, which we call point P. And then we reduce this whole triangle just to the line on which P lies. And then we go in the direction of minus P here to find the next vertex, which is in the direction of point A. This creates, again, another triangle. And we just repeat the same steps again. We try to find out what is the minimum nearest point from A to P. Once we find it, we try to reduce the triangle. In the next step, we try to move along this minus P direction to find the next vertex. And if the next vertex does not increase here or create a new triangle, then we are done. And P is basically the nearest point to A. And this is roughly the inner workings of this GJK algorithm. And now the question is, how can we actually use this algorithm, which only computes point to polygon, for doing polygon to polygon collision checking? And so for that, I have a small animation here where we have a green triangle and a red triangle, and we want to know, are they actually in collision? And the most important idea here is that we are actually check if the Minkowski difference contains the origin. And of course, the two questions here are, what is actually the Minkowski difference, and why does it have to contain the origin? So yeah, the definition of Minkowski difference is basically just that you take all the combinations of points in A and B, and you take just the difference between them. And so for our example here, the Minkowski sum would look like this. So we take basically all the points in the red triangle, we take all the points in the green triangle, and we just add them up. This would create you the Minkowski sum. And now to create actually the Minkowski difference, we just take the minus here. So you see here for each point here on the green triangle, we just subtracted all the points here on the red triangle. You can see here the vectors for the red triangle, they are basically just the minus vectors here attached to the green point. And so this creates here the gray area of the Minkowski difference. Okay, and so if actually the polygons overlap, then there needs to be one point where, of course, the difference between those 2 points is 0 because, yeah, of course, they are the same points. They are in both triangles. And that is why, if they are actually overlapping, then the origin needs to be inside of this Minkowski difference. And consequently, A and B share a point. So yeah, if they overlap and we draw the Minkowski difference, then you can see here that the origin is actually inside. And this is only true if they're actually overlapping. And so that is basically the whole idea of this reduction from polygon to polygon towards point to polygon. So instead of doing something complicated, we can already go back to the GJK algorithm and now compute, is the origin actually inside of this Minkowski difference or is it outside? Okay, so that is the whole idea of this reduction, whereby, yeah, as I already said, the point is the origin and the polygon is the Minkowski difference. And if you can verify that it's inside, then you know that they are in collision, and you have just proven that 2 collision pairs collide, and you can say, okay, my configuration here, there's a collision between 2 collision pairs. So luckily, this has all been implemented, and you can find it in this flexible collision library, which is open source. It's super easy to use. So basically, you just have to create 2 collision objects. You have to create a request where you specify some parameters, and then this distance function here from FCL will give you just the result here. And in the result, you can just see, are my 2 collision objects in collision or are they not in collision? And under the hood, of course, the GJK algorithm is used, the Minkowski difference is computed, but this is all something you don't really necessarily have to take care about. Okay, right, and here are some more links. So this whole animation which I showed you is also from the internet here, and there's also a good video on YouTube which can show, which you can see to understand this a bit better. Okay, any questions about computing collisions? Yes.
N times m, like won't this be a little bit inefficient?
Well, this is just the most efficient algorithm we have right now. Yeah, but you're talking about the combination of edges, right? And how this would be actually the resulting Minkowski difference would have like the combined number of them, right? Yeah. But yeah, it turns out that it's actually very difficult to just check if two polygons overlap. So basically, I think there are other ways where you start with 2 points in each of the polygons and you try to move them closer to each other. But yeah, it turns out that it's easier to just compute the Minkowski difference and then run this GJK algorithm. Okay, any other questions? Cool, okay. Then the last topic for today will be stability constraints. So we talked about that the robot should not be in collision with obstacles. Now we want to talk about how can the robot actually make sure that it's not tipping over. So this is only relevant, of course, if you have a walking robot like this humanoid here or this quadruped, and you want to classify again if a configuration is actually valid or not. And for that, we use this definition of static equilibrium, where we basically just say that the robot body is at rest when the sum of forces acting on the robot is 0. And as a constraint function, we take just a function which tells us is statically stable, which is again in this formulation of our constraint functions, which tells us true or false, and which tells us is a robot at a specific configuration Q in static equilibrium or is it not. And I just want to give you a small idea of how this actually is computed. So let's say you have this animation here of this humanoid robot, and you assume that it's in a uniform force field like in gravity. That means that at each point of the robot there is a force acting on the robot and it's pulling the robot down. And one important consideration for computing static equilibrium is the center of mass. So the center of mass is basically just the mean location of a distribution of mass in space. So you can compute it by computing the overall mass of the robot here and computing the mass of each of the links of the robot and multiplying it by the radius from the center of mass, and you divide it by the overall mass of the robot. And this gives you the COM, or the center of mass. And if you have this, you can actually use it for static equilibrium. I would say the most important thing here is really that if you can actually support the robot at the COM, then the robot does not tip over. So this is basically the same idea for every rigid body. So if you have a rigid body and you just put something under this center of mass, like for example with this remote controller here, you can just balance it by putting something under the center of mass. The same applies, of course, to the robot. And I would say a little bit of a consequence here is also that if you add counter forces to all forces relative to the center of mass, then the robot does not tip over. So for our case here, this would mean forces and rotational forces or torques can be just seen at the center of mass. And if we could stabilize those forces and torques here at the center of mass, then the robot would not tip over. And the way of how we can stabilize this is, of course, that the robot is somehow having different forces, for example, from the ground. Here there might be like a ground reaction force where the robot is just standing on something. And then we can project those forces to the center of mass. And if those forces act against the forces of gravity here, then the robot would be stable. So in this case here, you can see that we have one force going down for gravity, one force going up, and there would be maybe a slight force going into the right direction, which means that the robot is maybe sliding down here. But if you have also friction. If there's some friction force here and it projects to the center of mass and it balances everything out, then the robot would be in static equilibrium. And so basically the idea here is just that you analyze all the forces which currently act on your robot at the center of mass, and if they all balance out, then this robot is stable and it will not tip over. And yeah, just as a summary here, so is you assume that the robot body is at a configuration Q, you approximate the robot as a single rigid body, you compute all forces and torques acting on the robot body, you sum them up relative to the center of mass, and as the sum is 0, then the robot is statically stable. All right, and I would say the most fundamental paper on this topic is by Timothy Brattle, Testing Static Equilibrium for Legged Robots, which you can also read here. Yeah, and that's basically all for static stability. Any questions about this? Cool. Okay, then let me just recap everything we did today. Yeah, I would say we started with this big idea of modeling robots as points in configuration space. This idea from Tomás Lozano Perez, which is really at the heart of motion planning, which is really the most fundamental idea in motion planning. Then we talked a little bit about topology as a tool to model configuration spaces, how you can take an arbitrary robot, analyze all its joints, transfer it to mathematical space. Then we talked about distances, how you can actually apply a metric on those configuration spaces, which measures distances. And finally, we talked about applying constraints and having efficient evaluation functions. We only talked about collision checking and static equilibrium, but of course there are also other constraint functions which you can apply depending on whatever task you want to achieve. And yeah, I think also super important was this GJK algorithm for collision checking of convex objects, because it's really at the heart of a lot of collision checking algorithms. And yeah, collision checking and avoiding of obstacles is of course one of the main constraints in robotics. Okay, and next time we will talk a little bit about using discretization of the configuration space to find paths. This will bring us a little bit to discrete graph search and to A star and to finding paths optimally with A star. And also we will go a little bit into the topic of admissible heuristics. So yeah, and here are also some additional links for you where you can just read a bit more about the topics of today. And also I would say those are the most important publications on which this lecture is based, especially this planning algorithms book from Steve Laval. This is really the Bible of motion planning, I would say. Okay, any more questions about this lecture? Yes, please.
I'm still a bit confused about like where would we introduce the joint limits formally? Like would you filter the target point, or would this be a constraint, or where would you introduce them?
Yeah, so this would be basically a constraint.
Okay, so as a
Yeah.
And then another question, maybe like if you were to like wanted to like energetically optimize your joint motions.
What was the word?
Like if you like want to reduce energy consumption for joint
Mhm.
motions.
Yeah.
Could that be implemented as like a metric, or where would you separate this?
Yeah, so this would be basically something which we call an optimization objective, where we want to just prioritize different paths. So for example, in that case, you don't want the shortest path, but you want like the energy minimized path. And that would be a topic for optimal motion planning, and this will come in a later lecture. But of course, with the metric, you already like you already try to like bias paths into a direction of a certain objective. And so, for example, if you have a metric which gives you smaller distances for low energy paths, then of course you would maybe try to do this metric because it would give you more often like paths which gives you lower energy. Yeah. Any more questions? Okay, then thank you everyone and see you next week.